All right, let's now write this out entirely in terms of matrices, getting rid of this summation over elements. All right. Okay, in order to do that, what we get is our big vector C2, C3, C4, C5, C6, so on until we come to the last element C2NEL minus 1, C2NEL, C2NEL plus 1. Okay, now in order to write this, allow me to assume that every element, or allow me to consider the case where every element has the same length. Okay, so if HE equals H for all E. Okay, that's the case I'm considering. It just makes it a little more, makes what I have to write a little less cumbersome. Right? In particular, what it does is that it allows us to write here 2E A over HE. Okay, sorry, over H, as we've just agreed. Right? Now, we are going to write out our big matrix, giving myself plenty of room. Okay, for the very first element, we have contributions only from C2, C3, right? And if you go back and look at what we had on the previous slide, allow me to just pull it up for a second, right? Okay, look at the contributions from C2 and C3 on the left-hand side here. Okay, we get here minus 4 over 3, 8 over 3, minus 4 over 3, and here we get 1 over 6, minus 4 over 3, 7 over 6. Okay, we move on to the next element. Element 2 has contributions from C3, C4, C5, right? Or alternately from global nodes 3, 4, 5, global degrees of freedom 3, 4, 5. Okay, it is going to get slotted into these positions here. Okay, right? That's where the contribution from C3, C4, C5 will come. All right. Now, the contributions on the side of columns will come in here, right? Which will come all the way down here, right? It'll come all the way up to this column and to the next two. Okay, so what that means is that when we come here, we add on 7 over 6, right, from the 1, 1 component of the stiffness matrix of element 2. And because I need a little more room here, let me move these arrows across a little. Okay, so we get 7 over 6, and then the rest of that, of the stiffness matrix of element 2 just fills itself here. Minus 4/3, 1 over 6, right? We get here minus 4 over 3, 8 over 3, minus 4 over 3, and here we get 1 over 6. We get minus 4 over 3, and here we get 7 over 6. Okay, the important thing is that that is where the contribution from the common node or the common degree of freedom of elements 1 and elements 2 comes about, and that is from that degree of freedom. Okay, the process continues, of course, until we arrive at our very last element. Okay, and for it we observe that it's going to form this little block at the very bottom of the bottom right of our matrix. Also observe that as we go on to element 3 and so on, we are going to add some more terms here, right? That's where terms are going to get added, right? That's where components are going to get added into the stiffness matrix. When we come down here to our very last element, NEL, we see that it will give us a contribution 7/6, but that contribution itself will be added on to a contribution that was already put in there from element NEL minus 1. Okay, so we'll get 7/6 here, minus 4/3, 1/6, minus 4/3, 8/3, minus 4/3, and here we get 1/6, minus 4/3, and 7/6. Okay, the D vector here is full, right? It starts out at D1, D2, D3, D4, D5, and D5 is the last trial solution degree of freedom for element 2. Okay, we carry on until we come here to D, 2NEL minus 1, D, 2NEL, and D, 2NEL plus 1. And all of this then gets closed. Okay, so that is our stiffness matrix, right? Okay, or those are the contributions from the left-hand side term of the weak form. All of this now equal to, on the right-hand side, again our C vector just as before, C2, C3, C4, C5. We go on until we come to C2NEL minus 1, C2NEL, and C2NEL plus 1. Right? Now, there are two types of terms which need to go in here, right? The contributions from the forcing function as well as the contribution from the traction. Okay? So, I will open a parenthesis here. Since I've allowed us to assume that we have a fixed element length, we don't have to use HE, we use H instead. Okay? Right? Which is uniform for all the elements. It's the same element length for each element. So, we get a contribution FAH/2, and now we get our vector from the forcing function. For element 1, because those are the only degrees of freedom from the weighting function, we go back and look at the way we wrote out our vector from the forcing function. We get 4/3, okay, we get 1/3 from element 1. We come to element 2, and those are the contributions, okay, from the weighting function degrees of freedom. Right, and if we go back and look at how we wrote the sum over elements of the contributions from the forcing function, we see that we do get indeed a 1/3 being added here. We get 4/3 from the C4 degree of freedom, and we get a 1/3. But this 1/3 will then be joined by another 1/3 from element 3. Right, and this process continues until we come all the way down to the contributions from the last element. Okay, the contributions from the last element will have the first node from the last element will give us a contribution of 1/3, or the first degree of freedom will, but it will be added on to an existing contribution from element NEL minus 1. Second degree of freedom gives us 4/3, and the very last degree of freedom gives us 1/3. Okay. This vector then contains the contributions from the forcing function. For the traction, remember, if you go back and look at the way we wrote out the traction vector contribution, down here, it's the very last term on this slide. The only contribution comes from C, 2 NEL plus 1. Okay? Since we have the entire C vector sitting here, what that tells us is that in order to write the traction contribution as a vector also, we fill it with zeros all the way down except for the very last component, which is TA. All right? So that we need to close a parenthesis. Okay, so this is, now if we go back and look at the matrix that we have on the left-hand side here, we sum over, we add up the terms that needed to be added. Likewise, we add up the terms that need to be added here. We end up with a matrix vector problem. Okay? One thing I want you to note, and this is what we're going to pick up when we start the next segment, is that the length of this vector is what? How many components in that vector? 2 times NEL. Whereas that vector has 2 times NEL plus 1. Consequently, this matrix that we have here is 2 NEL times 2 NEL plus 1. Right? This vector again here is 2 NEL. Each of those vectors here, right? Each of those vectors is, however, okay, of the same length, right? Because they're forming a sort of dot product with the C vector. All right? So we're going to use this when we return to the next segment.